Good morning, students. So, in the previous lecture, we were discussed about reflection and transmission at normal incidence, and today I am going to discuss about reflection and transmission at oblique incidence. So, before that, I want to tell you that reflection and refraction of EM waves of light at a plane surface between two mediums of different dielectric properties are a very familiar phenomena to you. So different aspects of the phenomena divided into two classes. First one is kinematic properties. Okay, and the second one is dynamic properties. Okay, so in case of kinematic properties, our laws of reflection and refraction are studied. So that is the angle of reflection equals to angle of incidence. That is first law of angle of that is first law of reflection, and second is Snell's law, that is law of refraction. What is Snell's law? That is sine of angle of incidence to the ratio of sine of angle of incidence to the sine of angle of refraction is equals to the ratio of the refractive indices of the mediums. Okay, so I and R, in case of reflection, R is angle of reflection, and in case of refraction, R is angle of refraction. And second law of both, that is common, that is all incident ray, normal, reflected ray, refracted ray all lie in the same plane. So these come under kinematic properties. Second one is dynamic properties. Under this, we studied intensities of reflected and refracted radiations, and phase changes and polarization. So now we start with the reflection and transmission at oblique incidence. So here incident ray strikes at the interface at an angle. So okay, so this is, so here we have incident ray that makes an angle theta I, and this is wave vector, this first medium, second medium. So from here, this is our reflected ray, makes an angle theta r, kr, it is wave. So here wave travels from first medium to second medium, and it is refracted or transmitted wave making angle theta t, wave vector k. So this is plane of incidence. Okay, so what happens here? Here the incoming wave meets a boundary at an arbitrary angle theta I. So here we suppose that a monochromatic plane wave, that is EI RT equals to E0I exponential iota Ki dot R minus omega t, and Bi RT equals to 1 upon V1 Ki cap cross EI. So this is equations for incident wave approaches from the left, okay, and gives rise to a reflected wave as we seen in the diagram above. Okay, so this is giving rise to a reflected wave making angle theta r, and a transmitted wave that is making angle theta t. Okay, so now we write the wave equations for these. So this is equation for incident ray, and now reflected ray, er rt equals to e0 r exponential iota kr dot r minus omega t br rt equals to 1 negative, because the direction is opposite, minus 1 upon v1 kr cross er. Okay, so this is our equation number second. So third is equation for transmitted wave, et rt equals to e0t exponential iota kt dot r minus omega t, and bt rt equals to b0t, sorry, we have to write it in the previous form as the equations is written above. Okay, so what is the value? 1 upon v2 kt cap cross et. So this is our transmitted wave. So all the three waves have the same frequency. All the three waves have the same frequency omega. So the three wave numbers are related by the equations as that is ki v1 equals to kr v1 equals to kt v2, which is equals to frequency omega, or ki equals to kr equals to v2 upon v1 kt equals to so as we know that the ratio of the velocities is equals to the ratio of the refractive indices in the reverse order. So this is equals to n1 upon n2 kt. Okay, so the combined fields in the medium must be joined. Okay, and to the fields et and bt in the medium too. So in the combined fields in the medium one, that is ei plus er and bi plus br. Again, so and in the second medium we have the fields et and bt. Okay, so now again we are using the boundary conditions used previously. So these boundary conditions are, first one is epsilon 1 e perpendicular 1 equals to epsilon 2 epsilon 2 e perpendicular 2. Okay, so second one is b1 perpendicular equals to b2 perpendicular. And third one is E parallel 1 equals to E parallel 2. So fourth one is 1 upon mu 1 V1 parallel equals to 1 upon mu 2 V2 parallel. Okay, so using these boundary conditions we get the journal generic structure. That is what we get. Here we have coefficient into exponential iota ki dot r minus omega t plus exponential iota kr dot r minus omega t equals to, here we have the coefficient exponential iota k t dot r minus omega t at z equals to 0. So here x, y and t dependence is confined to the exponents because the boundary conditions must hold at all points on the plane. Okay. So otherwise a slight change in x will destroy the equality. So the time factors are already equal. So for the spatial terms we have ki dot r equals to kr dot r equals to kt dot r when z equals to 0. Okay, so for all x and y. So here this equation can only hold if the components are separately equal. Okay, so for if x equals to 0, then ki y equals to k r y equals to, this is r and this is kt, that is y components are equals. Okay, and if y equals to 0, what we get? We get the x components. Okay, y equals to 0, what we get? kix equals to krx equals to ktx. Okay, so if x's are oriented so that ki lies in the xz plane, that is k, that is k k, sorry, there's some problem in the pen. K I y equals to 0. Okay, so then according to this equation, what we conclude here, according to this equation, if ki y is equals to 0, then kr y and kt y is also equals to 0. So what are the conclusions from here? There are first law, incident, reflected and transmitted wave vectors form a plane called the plane of incidence, which also includes normal to the surface, that is here z-axis. So equation implies that ki sine theta I equals to kr sine theta r equals to kt sine theta t. Okay, where theta is the angle of incidence, theta r is the angle of reflection, theta is the angle of transmission, more commonly known as the angle of refraction. Okay, so all of them measured with respect to the normal. Okay, so this is that all lie in the same plane, that is on z-axis, x-ray plane. So in second law, angle of incidence is equal to the angle of reflection. So here, so previously we have written that ki equals to kr. So that means if ki equals to kr, that means sine theta I equals to sine theta r, and sine of two angles is equal only when the angles are equal, which implies theta I equals to theta r, that is angle of incidence is equals to angle of reflection. So this is a law of reflection. So again, as for the transmitted angle, what we have, sine theta I equals to sine theta kt sine theta t. And again, previously from equation 4, what we get, that ki is equals to n1 upon n2 kt. So from here, sine theta I upon sine theta t equals to kt upon ki. So kt upon ki is equals to n2 upon n1. Okay, so that is a ratio of the two mediums, and which is a Snell's law, law of refraction. Okay, so we get the different laws. So these are the fundamental laws of the geometrical optics. Some specific boundary conditions have to be found according to equations. Okay, so any type of wave can be expected to obey the same optical laws when they pass from one medium to the another. Okay, so we have previously written that exponential equation generates structure. So according to that, exponential factors cancel out and boundary conditions becomes what we get. First one, epsilon 1. Okay, so here we have electric field on the one side, that is combined field E0i plus E0r. Okay, and the z component equals to epsilon 2 E0t. Okay, so second equation gives us, second boundary condition gives us B0i plus B0r z equals to B0t z. Okay, third equation, third boundary condition gives us E0i plus E0r. Here we have xy components equals to E0t xy. And last fourth one is 1 upon mu1 V0i plus B0r xy equals to 1 upon mu2 B0t xy component. So where B0 equals to 1 upon B k cap cross E naught in each case. Okay. So last to represent pair of equations, one for x component and one for the y component. Suppose that the polarization of the incident wave is parallel to the plane of the xz, plane of incidence, that is xz plane. Okay, so here we draw it. Okay, so here again we have incident wave. So this is our EI, this is BI, and all are perpendicular to each other. Then this is KI. Okay, so first medium, second medium. So here we have reflected wave, and this is components KR. Remember that all the three are perpendicular to each other. So this is BR. This BR component is not in the plane of the paper. Okay, so that's here angle theta R, here angle theta I, Z axis X. Okay, so here transmitted wave theta T. So here components ET, KT, and this is ET, and this is angle theta T. Okay, so it follows that the reflected and transmitted planes are also polarized in the plane. So here we have components that resolved. So from boundary conditions we have just written above. See these boundary conditions. We have to apply the values of fields E0I, E0R, Z. Here we have to put Z component. Here we have to put X or Y components. Okay, so let's see what happens. So you can see here that this is our Z direction, X direction. Okay, so here this is KR. So KR, if we just checking the directions, this is KR. So KR makes angle theta R. Okay, and ER is perpendicular. So this angle is 90 degree. So we have to find the this angle. So it makes a linear pair. So that means theta R plus 90 degree plus let it be angle X plus angle X equals to 180 degree. Okay, so angle X is equals to 90 minus theta R. Okay, means what we have here, if we resolve the components. Okay, so this is our ER, which makes an angle 90 minus theta R. Okay, so as we know that here we have cos component, so we have cos 90 minus theta. Okay, and here we have sine 90 minus theta. Okay, so that means this is cos theta and this is sine theta. Okay, so accordingly all the angles of that is of theta, eta, et, that is a component of et, e0t and e0i along x and y. We can easily find the components of reflected fields and transmitted fields accordingly. Okay, so now we have to put the values in our boundary conditions. Okay, so what we get? First boundary condition implies epsilon 1. Negative signs are according to the directions. E0i sine theta I plus E0r sine theta r equals to epsilon 2 minus E0t sine theta t. Okay. So negative sign according to directions as we know. So second boundary condition adds nothing because the magnetic fields have no z components. Now third boundary condition implies E0 I cos theta I plus E0 R cos theta R equals to E0 T cos theta T. Okay. So fourth boundary condition gives us 1 upon mu1 B0 I plus B0 R equals to 1 upon mu2 B0 T. So here we are going to put the value 1 upon mu1 upon 1 upon B1 Ki cross E0 I minus K R cap cross E0 R equals to 1 upon mu2 B2 KT cap cross E0 T. So these are the equations we get after putting the values of the components of fields on the two sides. So as K and E are perpendicular in each case, so K cap are unit vectors. So K cap cross E is equals to unit vectors magnitude 1, its magnitude E0 sine 90. So this is equals to okay. So given the laws of reflection and diffraction, the fall of boundary conditions reduces to. So first boundary condition we have epsilon 1 E0 I sine theta I minus E0 R sine theta R. So as we know that as we proved above that sine theta I is equals to sine theta R, so we can write here as sine theta I equals to minus epsilon 2 E0 T sine theta T. Okay, so here we have taken out the negative sign, so negative sign cancel out and E0 I minus E0 R. So this is equals to epsilon 2 upon epsilon 1. So here we have sine theta T upon sine theta I into E0 T. So as previously we have showed that sine theta T upon sine theta I, this is equals to n2 upon n1 according to Snell's law. So what we get? E0 I minus E0 R equals to epsilon to epsilon 1 into n2 upon n1, that is equals to beta E0 t, where beta is equals to epsilon 2 upon epsilon 1 into n2 upon n1. Okay, and similarly the next equation, that is 1 upon mu 1 v1 E0 I minus E0 R equals to 1 upon mu 2 v2 E0 t. From here we get the similar equation, that is we getting about. Okay, so next boundary condition reduces to E0 I cos theta I plus E0 R cos theta R equals to E0 t cos theta t. So as we know that theta I is equals to theta, that means cos theta is also equals to cos theta R. So what we get here, E0 I plus E0 R equals to cos theta t upon cos theta I into E0 t. So again cos theta I, so cos theta t upon cos theta I, let it be equals to alpha. So what we get? We get two equations. One is E0 I minus E0 R equals to beta E0 t, and second one is E0 I plus E0 R is equals to alpha E0 t. Okay, so we solve the two equations for E0 I and E0 R as we done in previous cases. Okay, so here we have E0 I plus E0 R equals to alpha E0 t E0 I minus E0 R equals to beta E0. So cancel out 2 E0 I equals to alpha plus beta E0 t. Okay, so E0 t equals to 2 upon alpha plus beta E0 I. So we multiply equation this with beta and this with alpha and then subtract. Beta E0 I plus beta E0 R equals to alpha beta E0 t, and second equation alpha E0 RE minus alpha E0 R equals to alpha beta E0 t. So on subtracting negative, positive, negative, this cancels out. So here we have beta minus alpha E0 I plus beta plus alpha E0 R equals to 0. So here we have E0 R equals to, so if we take to the other side, we get the negative sign, so it becomes alpha minus beta. So what is, we have alpha minus beta upon alpha plus beta into E0, and that is the reflection amplitude. Okay, on solving, we get the values for E0t and E0r in terms of E0i. So further we discuss it in our next lecture. So have a good day.